So good morning to everybody. I will be doing the chairman as an emergency case, as always. The last day is there was one because some people are dropping. So let's start immediately introducing Mr. Kenji Kawabata from JGC Holdings Corporation, Vice President of Sustainable Project Sales. He is going to present us technology deployment, development, and demonstration for large-scale ammonia cracking. Please, Mr. Kawabata, go to the podium.
Thank you, Chairman. Good morning, everybody. My name is Kenji Kawabata, Vice President Sustainable Solutions Projects Sales Department from JGC Corporation. I'm honored to be presenting our technology here in international conference. Today, I'm going to talk about development of demonstration for the large-scale ammonia cracking technology. Actually, this technology is still under development phase, but I expect to be released commercial ready soon. So I have three agendas today. The number one is JGC Corporation introduction. Second, JGC hydrogen-related activities. And finally, I'd like to talk about the JGC large-scale ammonia cracking technology development. So let me first give you a brief introduction of JGC. JGC is a worldwide engineering and EPC company with outstanding records in the field of energy projects, including LNG, refinery, petrochemical, and now expanding its business field into the sustainable solution spaces like hydrogen, ammonia, CCS, and so on. So JGC's strength is project execution and project delivery capability for large and complex projects, experience in more than 20,000 projects in more than 80 countries. So we can leverage its know-how to any kind of project with global workforce of more than 9,500 qualified manpower. Also, JGC has more than 20 affiliate companies and provide engineering service besides the client at any time. So in India, we established JGC India in Chennai 2023. Currently, JGC India has about 500 manpower, which is providing any kind of engineering services as high-value engineering center for JGC Group. Their vision in the near term to be an EPC company and deliver the project for the local needs. From next slide, I'm going to talk about ammonia-related activities. On this slide, I'd like to introduce Ammonia Alliance Japan, which is a business alliance between JGC and Toyo Engineering. JGC and Toyo has jointly entered the business alliance for the fuel ammonia project utilizing KBR's proven ammonia production technologies. By combining the strengths of these two companies with KBR's license process, AJ aims to provide reliable and competitive solution for the global ammonia markets. Here you can see the key strengths of each companies. So JGC brings extensive experience in the large-scale projects and the modular construction. This provides reliable and flexible EPC execution at any time. So Toyo Engineering contributes deep expertise with KBR process plants, having experience in more than 80 ammonia projects worldwide. This ensures strong technical capability in ammonia process. By combining capabilities, AAJ can provide a one-stop, high-value solution from early planning phase to EPC phase. This slide shows JGC's in-house simulation tool named GAPAO, which stands for Green Ammonia Plant Automated Optimizer. GAPAO is a simulation tool to optimize the green ammonia plants by considering the fluctuating renewable power input while balancing the hydrogen production, the power consumption, and the plant dynamics. The center shows in the main graphic interface where you can set the condition and run the simulation. The other shows the simulation outputs such as hydrogen balance simulation on the top left and the block flow diagram on the bottom. GAPA also provides a levelized cost breakdown, allowing the user to evaluate the economics performance of a different scenario. Like this use case, GAPA enables integrated optimization of the green ammonia plants, considering the technical and economical prospects, especially under fluctuating renewable energy conditions. So this is our green ammonia demonstration plant in Japan. In this demo plant, we demonstrated integrated control system from power input all the way to the ammonia production as shown in this diagram. The electricity from the PV power and the grid is sent to the water electrolyzer to generate the hydrogen. Then the hydrogen is supplied to the ammonia synthesis unit. The nitrogen is supplied separately and fed into the synthesis process. The produced ammonia is delivered by the liquid ammonia truck to the various users. Actually, this demo plant has just plant operation started, and now we are collecting the data to establish a reliable green ammonia project. So our integrated control system architecture is explained in more detail in this slide. The goal of this system is to maintain the hydrogen supply efficiently and to maintain the optimal plant operation even when renewable power input is unstable. By minimizing downtime and stabilizing the production, the system enables continuous and cost-effective green chemical production such as ammonia. On the left-hand side, renewable energy power information such as power output capacity, historical weather data is fed into the integrated control systems. Our system is linked to is a distributed control system in the chemical plants. So based on the power availability and operation status, the control integrated system adjusts the hydrogen production, the hydrogen storage levels, and the plant load, ensuring the stable supply of both hydrogen and production. Through this study, integrated approach, we aim to demonstrate a next generation control system for the green chemical plant stable operation. Okay, now I'm going to explain our large-scale ammonia cracking technology development. Needless to say, Japan is an energy importing country and aiming to reduce the greenhouse emission by 46% compared to 2013 level by 2030. To achieve this target, Japan is struggling to import of 3 million tons per annum of hydrogen by 2030. As you know, there are several hydrogen carriers being studied, such as ammonia, liquid hydrogen, and MCH. JGC is providing engineering service for any kind of carriers, while we are developing ammonia cracking technology as a technology supplier. Actually, this program is proceeded under the support from NEDO, who is Japanese government agency, and aims to release it to the market as Japan technology. The project is organized by 3 Japanese companies, JGC, Kubota, and Taiyo Nippon Sanso, starting from fiscal year 2023 and will be completed by fiscal year 2025. JGC is responsible for the all over the process and improving performance of cracking furnace technology supported by Idemitsu Kosan. The Kubota is responsible for the cracking tube development, and Taiyo Nippon Sanso is responsible for the hydrogen purification technology development. This block flow diagram shows the overall ammonia cracking process systems. The process starts from the ammonia vaporizer to produce the cracking reaction efficiency in the cracking tubes. After the vaporization, ammonia is fed into the cracking furnace after the ammonia pre-cracking process. The cracking gas furnace converts ammonia into the hydrogen and nitrogen with some uncracked ammonia and cooling before purification. The off gas from the purification is used as a fuel for the cracking furnace. We have 3 objectives in our technology development. Number 1, overall system optimization to reduce the capex. Number 2, cracking tube material development to improve ammonia conversion rate. Number 3, efficient gas purification technology to improve hydrogen purity and recovery rates from cracked gas. I'm going to explain about 3 objectives in more detail from the next slide. So as for the system, overall system design, JGC is focusing on the entire efficiency improvement and optimum catalyst design since the selection of optimal catalyst and the process condition will be a key success factor to achieve the high ammonia conversion rate. So as shown in this sketch here, our cracking furnace applies external heated cracking types with top firing as same as steam reformer. The advantage of this design to enable the process temperature control, which ensures the uniform temperature distribution across the entire catalyst bed and the maximum reaction temperature. This approach is also well suited for the large scale up, then make it easier for the large scale up operation. Moreover, the system offers environment benefits because of CO2-free exhaust gas emission. The diagram on the center shows the laboratory test of the nickel catalyst in the cracking furnace, which indicates the tendency of the ammonia conversion rate against the temperature, reaction temperature. That we have tested catalyst performance by changing the temperature and operating pressure as parameter to understand the catalyst characteristics. The sketch on the right shows the CFD analysis for the cracking furnace inside. Since our burner configuration applies top firing, understanding the behavior of the reaction and furnace is important for the design optimization. The temperature gradient of the tube should be minimized for the effective conversion. Like this study, we have been demonstrating CFD analysis and feedback simulation results to our design. The technical challenge for the ammonia cracking process is night riding on the cracking tube. We shall overcome this issue to enhance the efficiency and the durability of the cracking process. Therefore, cracking tube material development will be a key success factor. Here is a just image of cracking tubes used in the steam methane reforming process manufactured by Kubota. These tubes are designed to withstand high temperature and harsh conditions to realize ideal ammonia cracking. The bar on the right compare the rate of the night riding formation among the different materials. The new catalyst which we are now developing on the right hand has a significantly lower rate of night riding and indicating the superior performance. We are also aiming robust tube material which also has a long design life, 15 to 20 years, compared to the typical 10-year design life. Cracking gas purification is also an important area of technology development. To increase the purity of hydrogen produced from the ammonia cracking gas, our system applies pressure swing absorption system for the separation and purification. This PSA technology is underdeveloped by the Taiyo Nippon Sanso, which removes uncracked ammonia and nitrogen from high pressure cracking gas using the single PSA unit to purify hydrogen effectively. Okay. So this is the key takeaways. Thank you for your attention.
Thank you, Mr. Kawabata. So let me now introduce the second speaker, which is Mr. Niraj Maurya, Senior Geologist in the Oil and Natural Gas Corporation Limited. Is going to present us the natural hydrogen potential of the northwestern Kudappa Basin, Andhra Pradesh, integrated geoscientific assessment and production pathways. Thank you, Mr. Niraj.
Thank you. A very good morning, everyone. I am Niraj Maurya, working as Senior Geologist at ONGC Limited, Dehradun. So I am actually very excited to share you all my research on this topic, that is natural hydrogen potential in northwestern Kadapa Basin in Andhra Pradesh, India. So the flow of the PowerPoint presentation will be starting from introduction to natural hydrogen, then to geological and geophysical methods by which we have identified the potential areas. Then we will come to the resource estimation of natural hydrogen, and finally to production pathways. So let's begin. Okay. So what is natural hydrogen? Natural hydrogen is the hydrogen which is produced due to geological activities occurring in the subsurface of the earth. It is also known as white hydrogen or geological hydrogen. Okay. So this is the cationic geological hydrogen model. What happens when water reacts with iron olivine at high temperature, that is about 150 to 300 degrees Celsius? It makes hydrogen as a byproduct. These reactions typically occur in about 6 to 15 kilometers in crustal depth. If above the zone of generation there is any sedimentary rock which are porous in nature, this hydrogen can accumulate there. And if there is ant seal and some trap there, then we can extract this hydrogen just like natural gas. For this to have economical sense, we need water supply to the basement, we need deep-seated faults, we need overlying cratonic basin. One of such basin in India is Kadapa Basin, where our study will be done. And this type of mineral, which is called phyllite, they are present in ultramafic rocks. This type of rocks are present in Archean greenstone belts, which are part of cratonic areas. One of such greenstone belts are there in Dharwar Craton, where the Kadapa Basin sits. So, coming to the next slide. Okay. This is geological map of Kadapa Basin. In the geological map, you can see there are 5 greenstone belts in the periphery of Kadapa Basin. They are marked in green colors. So, for finding of the sweet spots, what we need to know is where the greenstone belt is extending in the basement of the basin. For this, we have done gravity studies. What happens is that greenstone belts have higher density than the surrounding rocks. So they have positive gravity anomaly. And from the gravity anomaly, we have identified one of such greenstone belts is extending beneath the basin, which is marked in black circle in the second picture. In the same area, we also have one seismic line, which is shown as XY in the first image. In the seismic section, we can see there is one high amplitude feature in the basement, which it is corresponding to the high gravity anomaly area, which we are interpreting as greenstone. In top of this, we have basin rocks, and there are deep-seated faults which are extending to the basement, which can act as water conduit. To know if any hydrogen is really being generated here or not, we have also done remote sensing and satellite-based analysis. From the remote sensing and satellite-based studies, we have seen in the identified area, there are several subcircular depressions which are occurring here. These are also known as fairy circles in the literature. These are about 80 to 100 meter or 160 meter in diameter, and they are very shallow, about 1 to 2 meter depth. And they are worldwide known to occur adjacent to non-hydrogen producing areas, and they are also used as proxy for hydrogen exploration. So in the area, we have identified these features. So these confirm that, okay, hydrogen is really being generating here. So now come to resource potential estimate. The data we gathered from geological and geophysical studies, we tabulated in this table, and we use this table to carry out Monte Carlo based simulation for resource potential of natural hydrogen. We use this formula for total hydrogen generation resource potential. We calculated the resource in MMTOE, that is million metric ton of oil equivalent, and BCM. So this is the result what we have. So I am very excited to share the result actually. The P90 potential in the area which we have identified is about 14 mmTOE. So P90 basically means in the 50,000 runs that we have done in the Monte Carlo simulation, 90% times the result is greater than 14 mmTOE. And for context, India's crude oil production annually is about 30 mmTOE. It's about half of India's crude oil production. The P50 estimate is about 37 mmTOE, and P10 estimate, which is about 88 mmTOE. we have also done sensitivity analysis as part of our study. From this analysis, we could see the hydrogen yield factor has highest sensitivity towards the end result. The second most sensitive factor is greenstone belt thickness, and third is olivine content in the ultramafic rock. So now finally coming to production pathways. Okay, we find the hydrogen, how to extract it. So basically, there are two approaches for this. What we could do is just do a detailed 3D seismic survey there and drill the well on the suitable trap and extract the hydrogen. But in this case, the flow will be not very high. If you see all the analogous basins worldwide, the flow is not very much. Alternatively, what we could do, we could drill injector wells directly at the greenstone belt and hydrofracture this. After this, inject water and steam. This will enhance the serpentinization reaction and enhance the hydrogen yield from the area. This way, we can extract the hydrogen at a much greater, what you can say, flow. So, as we can see, the integrated geological and geophysical data sets and interpretation what we have done, by which we have found deep-seated hydrogen producing lithologies beneath the Kadapa basin. The residual gravity high and the high amplitude reflective seismic feature validate that there is a feature which can produce hydrogen. The fairy circles which we have identified using remote sensing and satellite-based data analysis, it confirms that active hydrocarbon seepage is occurring in this area. Based upon our preliminary Monte Carlo-based simulation, the conservative estimate of geological hydrogen is there about 14 mmTOE, and P50 estimate is about 37 mmTOE. This hydrogen estimation is highly sensitive to hydrogen yield, greenstone belt thickness, and olivine content in the ultramafic rocks. So for the panel, we also have some recommendation. One of such is to have a policy to drill pilot wells to further enhance our interpretation or knowledge and see what is the reservoir characteristics there. Second, to have OLP like open acreage licensing policy for hydrocarbon like policies for hydrogen exploration also, so we can explore the hydrogen, because Kadapa basin is one of such study, but there are different ketonic basins in India also, like Bhima, Kaladki, Indravati, and they also have the same setup. And I think we could also do the same type of study and find hydrogen there also. And the third recommendation to the panel will be to have inclusion of natural hydrogen pilot projects under National Green Hydrogen Mission, because actually once you drill the hydrogen, it's very environmental friendly. And once you have drilled, the carbon emission is very low. And once you find a well, the production could be less, but it can generate hydrogen for about thousands of years. So this is a good thing. Generally, one oil well, we can produce oil for about 40 years. But in hydrogen, we could produce for thousands of years. So it's very sustainable and it's very green. That's all. Thank you.
Next presenter will be Mr. Terje Hawan, who is the Chief Technology Officer of SAID ES. He's going to present cold spark scaling non-thermal plasma methane, splitting the sustainable clean hydrogen and e-carbon. Thank you very much.
Good morning. Before we start, I want to have, an understanding of who's in the audience. So if you are working with natural gas or biogas, could you raise your hand? So 7, 8 people. Are you working with hydrogen, or do you intend to work with the hydrogen in the future? Or raise your hand. Okay, slightly more. And then I want to know if anyone believes in the idea of green hydrogen. So if you believe in the concept of green hydrogen, please raise your hand. The vast majority doesn't believe in green hydrogen, is my conclusion so far. So anyway, my name is Terje. I'm nice to be back here in India. I normally come to India twice a year to do talks on hydrogen conferences. And it's been changing quite a lot over the past years in India. 5 years ago, super hype about hydrogen. 4 years ago, super hype about green hydrogen. Today, less so. More realism, more understanding of what is going on in the big world. So my company, SIDE, if you wonder if it's short for anything, no, SIDE as a company, it is actually a word from the Viking area. So the Vikings, they had a Seid man or a Seid woman when they made these tourist trips to the UK. So Seid means magic and mystery back in the Viking age. And then the Northern Light was magic and mystery, thunder and lightning, magic and mystery. But we know it's science today. So we are bridging our Norwegian legacy with technology and science. So SIDE, what you see, the green dots, is installations we have made around the world for the past 28 years. So we have been in India since 2006. We delivered the first solutions to ITC in Bengaluru. And then our latest client in India is ArcelorMittal Nippon Steel. So what we do, I will be very brief. What we normally do is we deliver large-scale industry abatement solutions. So whatever industry, could be cement, could be coal-fired power plants, could be electronics, or it could be Coca-Cola factory. So what we come in and we alleviate that problem. We take away the emissions, so it could be NOx, it could be SOx, it could be CO2, or it could be PM. So the upper right picture is from Vizag installation we done for ArcelorMittal Nippon Steel, and where ArcelorMittal, they won a prize last year for best implementation of environmental technologies in India using our system to reduce the emissions from a large electrostatic precipitator. The key part here, as you will learn here, is the power systems. So what we do is to deliver very complex pulse generators. So electric pulse generators, high frequency systems, is the key on what we are doing. We also deliver these systems to marine engines. So in those cases, we reduce the particles, we reduce the NOx and the SOx, which will enable you to do carbon capture afterwards. Our technology is a pre-treatment step to make it possible to do CO2 capture. We also work with Nestlé, one of the Swiss giants, and this is what you see on the picture. You see our power systems on the right, and you see our what we call the reactor systems, coal plasma reactors. So this is what we've been doing. Hydrogen is nothing new. A lot of people seem to think there's something new with hydrogen and that it will improve in the future. So this was one of the first installations of scale in the world, 1927. Even today, that would be among the 10 largest installations of an electrolyzer in the entire world. And we're looking at close to 100 years later. Energy efficiency have improved about 5 to 6% since 1927. So a lot of people tell me, electrolyzers become much better. That's just bullshit, if you excuse my French. No, they haven't. They've become different, so they've been smaller, better densities, but the energy efficiency is guided by laws of physics, not opinions, not politicians, and not companies selling electrolyzers. So just to be very sure on that one. So the challenge of India, the challenge of Europe, the challenge of the world is hydrogen. If you just say green hydrogen, it's not like, hallelujah, we are saved because we have green hydrogen. That is a world of fairy tales and unicorns. And I live in a real world, in a real economy, where you need to pay for stuff. So if you're scaling hydrogen, you need to do it affordably. I repeat that again. You need to do it affordably. No business can afford paying 7, 8, 9 euro or dollars per kilogram of hydrogen. When you look at gray hydrogen, which is about 1.5 to 2, it's a silly dream to believe somebody's willing to pay double or 4 times for green hydrogen. So the case is very simple here. Here you need to understand the plus and minus with the different techniques. So the reality is electrolyzers are power and water hogs. They're consuming a lot of energy. The reason is simple. Water doesn't want to become hydrogen. You need to force it. Then in a later talk, you will hear more about steam methane reforming, which has been the standard for the last 70 years, but now is challenged because it's emitting CO2. Now you have a new problem. You need to have carbon capture and you need to have storage systems, which is making blue hydrogen, which is more expensive, obviously, than gray. And then what we are playing into is what we call methane splitting, methane pyrolysis, or turquoise, using natural gas methane, which you have today, which you have a global system for carrying, which you have a global system for trading, which is a standard all over the world as the starting point for hydrogen. The reason why we are in India is obviously you have now 6% natural gas in your system. Your Prime Minister has said we want to go to 15%. You also have the biogas potential, and you have one of the largest resources of coal bed methane. You just need a new technique to take the methane out of the coal seams, which you do not have at present, but will come in the next years. So what we are saying, we are looking at natural gas or methane. The obvious feedback I get from people is natural gas is bad because it's producing CO2. Yes, if you burn it. But we are proposing do not burn the natural gas, because then you get the problem, which is the CO2. So just imagine you have the methane, but you don't burn it. So what you do, you split the methane into the two core components, which is 25% of that is hydrogen and 75% of that is carbon. And when I say carbon, I actually mean real solid carbon. Carbon is not CO2. It is something elemental, and it's something we need in great doses. So what we are doing, we are exposing the methane molecule to a pulsating electric field. There is no catalyst involved. It's only a pure, simple 316 steel reactor system where we accelerate electrons and we bombard electrons against the CH4, and then we break it down into the core components, hydrogen and elemental solid carbon. The principle here is the power source. So unlike a lot of other companies, they rely on thermal or thermal catalytic. This is a cold system. The energy is generated by a very unique power system combining DC and AC in the same system and generating electrons which have sufficient energy to knock out the bond electrons holding the molecule together. So you can say it's a cold splitting of a molecule, or dry reforming could be another way of looking at it. So the bases are very simple. We use renewable power, energize the power system. We generate a constant flow of electrons about, we generate and stop 100 kilohertz, which is 100,000 times a second. We generate pulses, which is doing the splitting for us with no fancy equipment. And then we get the hydrogen, which is just like any hydrogen, and then we get the carbon. And that's the not well understood part, because the carbon is a high value product. In most cases, it's also larger value than the hydrogen. So in case you wonder about the science behind it, the science is called electron avalanches or Townsend avalanches. So the basics are you generate a very strong electric field, but not too strong. You don't go into arc, you don't go into spark, but you bombard the molecule with this, and then you have what we call an electron scissors, cutting the molecule and then generating the methane that way. The reason why we are doing this is because there is an infrastructure for natural gas methane in the world. 95% plus of all the hydrogen today is made from methane natural gas. That's a fact. It's not an opinion. The problem is for the world today is that we focus on CO2 as the problem. And that gave birth to the idea of green hydrogen, which was supposed to be, the savior, the superhero in the story, but it's not, because we realize the cost of the superhero is not affordable. So now people are starting to realize that green hydrogen is more dream, less reality. So this is something I don't claim myself. I also have the support from Hydrogen Europe, which is the largest hydrogen lobby in the world. They're saying, in order to reach green hydrogen, we need to be at certain scale of electricity. Green electricity needs to be abundant. It is not. It's not in India, it's not in Europe, it's not in the world. So what they're saying, we need a bridge. We need something to bridge that gap over time. And that's where methane splitting comes into the play, especially if you combine an electric system using renewable power, driving an affordable system, and then you take the best from both worlds. You take the natural gas, the methane, you expose it to electric field, and you use renewable energy to drive the system. Then you have the natural transition way, using electricity still, green electricity, and low carbon methane. I'm not going to dive into this one because the next speaker will look into it, but let's understand, I'm sharing this afterwards, so if there's any detail you want to know, I'm here, I'm green, easy to find, also in the Norway booth in hall number 2 afterwards. So there is some obvious advantages there. We don't use water in our system. We don't have any CO2 in the system. We call the system pre-carbon capture. So we capture it because it needs to be captured as a solid. So just fundamental physics. This is the only thing I want you to remember for the entire presentation. This is about fundamental physics. It's not about opinions, my views, or whatever politicians mean. The fact is, water electrolysis requires a lot of electricity because it's a very stable molecule. So in this case, you need textbook 39.4 kilowatt hours of energy to make 1 kilogram of hydrogen from water. The same if you have 1 kilogram of hydrogen made with methane pyrolysis, you need less energy. Textbook 5.2. We all know textbook is not the final answer, so it will probably be in the range of 10 to 12 for the upper one, and in the range of 50 plus minus for the second one. And that translates into lower carbon emissions in Norway. So we have 25% of the carbon emissions for the hydrogen made by natural gas or methane versus green electricity or green hydrogen. This is an eye-opener for a lot of people because they don't study it, they didn't see into the economics, and they didn't understand the fundamental physics which is guiding this. So remember, it's all about the bond energy. Imagine cutting a bread which is frozen versus a bread which is not frozen. There's 2 different levels of energy you need to put into that exercise. So in addition, what we are doing, we have actually 2 plus energy streams. So we can sell the hydrogen as any hydrogen, it's low carbon. We can sell the carbon, which is a high value. And also what we're seeing now more and more, we're getting carbon credits for not making CO2 and removing the methane permanently. So we get 3 revenues from the same product. So the case for India, why would you do this in India? Well, the hydrogen is obvious. I'm not going to talk about hydrogen, but I'm going to talk a bit about the carbon, because that carbon material is very unique. If you add that carbon material to, for example, concrete and cement, it'll become 40% stronger, tensile strength, compression strength, and you can also start to make carbon structures. So take away the steel rebars, replace them with carbon rebars, and you have buildings lasting for 5,000 years instead of 50 years. So it's not an experiment. We have been supported by the European Union. We have been supported by the Norwegian government. We are scaling this in Norway. The reason why we're doing it in Norway, we have the natural gas. 45% of Europe is coming from Norway, and we have the electricity. So it's the perfect location to start verify this one. So we already have an existing hydrogen hub where we're actually scaling this, and this is where we invite you to step in and have a conversation with us. Thank you.
Good morning to everybody. I'm going to present myself being without the chairman. So I'm Fabio Ferrari. I'm the head of the Circular Carbon Integrated Solutions department in SCAM, which is part of my group. So today, unfortunately, we're going back to the older technology after a very nice presentation from my colleague before. And we're going to make a comparison between different low carbon hydrogen generation technology, but much more closer to the conventional ones that actually are applied. First, let me introduce myself. We are a large company, an EPC contractor that is well known as Tecnimont in India as well, but we are also a technology company where Nescam is the one normally providing the services and the license and the technology to the rest of the company, and as well to many other clients that are willing to have us. We have a very large heritage in hydrogen production. We started since the earlies in doing hydrogen plants. We have more than 65 hydrogen production units using conventional technology, but we have never stopped in developing new technology and acquiring new competence in order to try to enlarge our portfolio, therefore providing different solutions depending on the different market situation. So we had an extensive literature about partial oxidation as well, and we are trying every time to improve the efficiency of the system and try to tackle the different requirements in the market, whether it is connected to the efficiency of production, the consumption of the feedstock, as well as the decarbonization of the plant itself. Just to introduce the three main topics on which we are going to go through, the presentation has a aim to try to evaluate and scout the different elements that are connecting the different technologies, but to leverage on the different advantages and the different peculiarities that can be introduced and then can be directly developed inside a specific plant, because we believe there is not a single solution for every problem, but we have many different solutions we can try to deploy in each context. So we're going to start with the steam reforming one, which is the most conventional one, the conventional steam reforming reaction inside a fire heater. Then going to the autothermal reforming, which is using air or oxygen in order to have on a catalyst the reaction itself. And the last but not the least, the one that we would like to try to introduce because it's the novel one, or at least less known, is the catalytic partial oxidation, which is, let me say, in the spectrum of possibilities, a novelty that is using oxygen or air in order then to have the reforming reaction without a flame on a catalyst bed. So let's start with something very simple. I believe most of you are already aware of. So we have the conventional steam methane reforming, which is the most implemented in refineries in different fields as front end of chemical plants. There are different optimizations that can be done, and of course it's very well known. The problem is the way to manage that type of technologies that we have a different presence of CO2, whether it is on the syngas itself, or if you want to have a complete removal of the CO2 in the flue gases that you have at the stack. Autothermal reforming instead is something that is, after a lot of time remaining a combined solution together with steam reforming, is now becoming something like a solution that can be implemented for very large facilities. So autothermal reforming is a technology where you have the reforming reaction happening on a catalytic bed, but there is no need for an external source of heat. So you have the flame, and then you have the conversion happening on a catalytic bed. That system now encompasses something like an advantage in terms of the fact that most of the CO2, almost all the CO2, it is only on the syngas, so that you can, through a pro-combustion carbon capture, try to remove that one. And then the ATR displays the highest efficiency in terms of energy consumption per tons of hydrogen to be produced. And then coming to the novel one, our little baby, the catalytic partial oxidation. This technology is using a different approach. Instead of having a flame to then provide the heat to the reacting element, we have a short contact time reactor bed. So the terms is in terms of milliseconds of permanence inside the catalytic bed, and it is the catalytic bed itself, the catalyst itself, that is a very high temperature, so the reaction are happening on the surface of the catalytic bed and remaining on the catalytic bed for very small time. This provides an additional element to go inside the reactor at lower temperature, providing a higher efficiency in order then to recover also the unconverted methane or unconverted hydrocarbons back to the system to improve the efficiency of conversion. So what I'm going to display, because as engineer we like numbers, so we cannot only make very fancy picture, we need to have some numbers to make the comparison. We are trying to describe the different cases in between a gray hydrogen, which is the conventional one, try to display the difference among them, and then try to see what is happening when going to blue hydrogen. Because we believe, again, we need to be very transparent and display the solution, and having such type of portfolio, we can try to drive that one. So using as benchmark, as base case, the catalytic partial oxidation, we're going to compare the different elements. So starting with gray hydrogen, you can see it through the numbers that the autothermal reformer has the lowest methane consumption. So if your aim is to have the minimum consumption of methane, you don't care about the CO2, this should be the solution for you, especially if you are going to very large capacities, because the ATR has the drawback to be 17% or 15% higher in terms of capex intensity. So if you can leverage on economy of scales, then of course, and you want to also have the lowest consumption, this is the solution you can implement. However, in terms of electricity consumption, if you sort out the air separation unit and you just make the comparison, consider a green electricity to supply the air separation unit, therefore your oxygen is already decarbonized, the comparison is that the electricity is more or less the same. Of course, lower than the one of electrolyzers, but comparing in between all the different solutions. In terms of decarbonization, you can see that having no possibilities to avoid and improve the system in terms of conversion, the catalytic partial oxidation displays a higher CO2 production in the system. The reason is that typically the CO2 emissions are directly connected to the enthalpy of the system. So if you consider the autothermal reformer, of course they will have the lowest one because it's having the highest efficiency, while in terms of then of efficiency you have the steam reformer and the catalytic partial oxidation. However, also for gray hydrogen, and if you consider 50 kilo normal cubic meter per hour, the CPO has the slightly less compact design. So for smaller capacities, if you have a problem of plot area, this solution can be again something that you can think about because still is efficient, but having also the advantage of the size. But now everybody, of course, is thinking about blue hydrogen. So gray hydrogen is something like the past for everybody, or at least we believe it is like that. So starting to introduce the point about the removal of CO2 and in any case to minimize the carbon footprint, because of course we don't have a solution that is totally removing the CO2 production. The point is that we need to try to have the lowest consumption, removing the CO upstream. By doing the removal of the CO2 in the syngas, then you have something like a cleaner gas, a cleaner tail gas. And that tail gas is then effectively to be recycled back to improve the efficiency. So if you make this type of assumption, you see that also the CPO that before was the one with the lowest efficiency has now the highest efficiency in terms of methane consumption. Therefore, the decarbonization becomes like something like an additional element of optimization of the performance itself. Then, of course, the air separation unit has an impact in between the different systems. So if you have a steam reformer, you don't have the need of oxygen, so you don't have to care about the separation unit. However, if you integrate the system, still a separation unit can be something like something you can provide to your system itself, especially in cases where maybe you need in any case to separate the air in order to have the nitrogen for the downstream units, like for example in ammonia production. Going in terms of efficiency, which is of course the hot topic, the real element of comparison is that when you're going to make a carbon capture, of course you will have the drawback of the energy consumption, which is a given. You cannot avoid that unless you have some more advanced technologies. In case of conventional technology or more new technologies, CO2 removal, it is of course a topic that has to be introduced, especially for very large existing facilities. The difference in between the possibility to have the pre-combustion carbon capture with respect to post-combustion carbon capture is that, just to give a number, the pre-combustion is consuming half of the total energy. So if you are able to have all the CO2 inside the syngas, you can halve your consumption in terms of recovery of the CO2 itself. Therefore, the CPO and ATR that has mostly the CO2 in the syngas, or in this case of the CPO only in the syngas, you can reach a very high removal of the CO2 itself with a lower consumption. Those, let me say, graphs are displaying this comparison to showcase that even if the CPO has a slightly higher CO2 production per consumption, it has a higher efficiency, and then it has the highest CO2 removal with the lowest energy consumption. Why? Because as I was saying before, having the technology, the advantage of having no flame inside the reactor and having a very low contact time inside the reactor itself, we can, through this reactor, have a very low inlet temperature that is approaching the system. So the feedstock should be preheated only up to about 350, 400 degrees C, while instead conventional autothermal reformer might be 550, 600 degrees C. Therefore, through self-recovery of the heat of production in the reaction, you can directly feed the feedstock to the reactor, therefore avoiding an additional fire heater, electrical heater, whatever is necessary to raise up the temperature up to the desired level. This allows to have only the CO2 in the syngas, therefore providing the highest recovery. last but not the least, I would like also to take the advantage of being here to present also the case of our pressurized autothermal reformer, which is an additional element of advantage, especially in cases where the ATR is displaying the highest advantage. So in case we are going to very high capacities in terms of hydrogen production for large facilities for production of hydrogen refineries, more or less the number is above 150,000 normal cubic meter per hour of hydrogen. ATR, it is displaying great economy of scale and great advantage in terms of compactness and efficiency of the system itself. While increasing the pressure of operation in our autothermal reformer, we have also the advantage of minimizing additionally the volume, because of course everything is sized by the volumetric flow rate. So by increasing most the pressure, we can also the possibility to shrink more the plant, so that even in case of 300,000 cubic meter per hour, we have a very compact design, a very simple unit, almost close by to the one of conventional ones for half of the capacity. So just to go into the conclusions, again, our company is having a large heritage of different solutions. We have tried to complement our technology with additional ones. We have provided additional solution to make everything more efficient. Indeed, we don't want to have a single solution for all the clients, a single solution for all the projects, a single solution for all the countries. The idea is to try to provide solutions that we can decide together and evaluate which is the most effective for you as a client, for you as a country, for you as a system. In this case, so I will try to showcase and display a mapping in order to help out in selection and understanding the technology. So just to go through it in a very simple way, if you're going to a very small capacity, that should be going to blue hydrogen, so the maximum achievable decarbonization, the CPO might be displaying the best results. Then we have a large span of opportunities of using conventional steam reforming technology, but the highest level of efficiency and the most updated cases in order to proceed in doing the design as before, but reducing the risk, we can also improve the efficiency. And then we have other solutions for very large facilities that, of course, will be sooner or later coming, even with conventional technologies, because again, there is not a single solution. So even high pressure autothermal reformer can be a possible viable solution for that. Our portfolio is so large, so the idea is let's try to discuss and evaluate the specific case. We are normally providing those services in understanding together since the beginning where to go, and then together we can guide you, combining even technology by others in order to achieve the solution you're willing to do. And capacity is one point, decarbonization is another point, but again, the plot area might be coming as an additional problem because maybe you don't have space. So we need to find a solution stretching the plant inside, and there is not a conventional standard plant. That's it. Thank you very much for your attention, and if you need anything, we are in all three as Maire to provide additional replies. Thank you again. So now we have our gentleman Inderjit Singh, which is the Chief Technology Officer of Green Hydrogen in Adani New Industries Limited, is going to present commissioning and troubleshooting of 5 megawatt of grid alkaline electrolyzer. Thank you for your presentation.
Yes, good morning everyone. My name is Inderjit Singh, and here I'm representing the Adani Group. So we are working under the Adani Group with the umbrella of Adani New Industries Limited. So Adani New Industries Limited is responsible to establish the green hydrogen and a derivative business, and directly Adani New Industries Limited comes under the umbrella of Adani Enterprises itself. As the government have targeted to decarbonize and align all the policies and the facilities with respect to carbon neutralities and take the target by 2070, in the same context, we are 100% aligned with the Indian government, and back to back, we also take this challenge and decide to establish the green hydrogen derivative under the umbrella of Adani New Industries Limited. Because it's a new challenge for the industry. So that's why we have decided first to establish all the concepts at a demonstration level, then after that go to execute at a bigger level. So in the same direction, we have decided to produce the green hydrogen through the water electrolysis system where everyone is targeting. So in the same direction, we have decided to commission a one green hydrogen generation facilities at the west coast of India itself. So first I just give you the glimpse that exactly what we have done. So to mature this, we have decided that a one electrolyzer stack with the alkaline technology of a 5 megawatt, where we can produce the hydrogen in a tone of 1000 normal meter cube per hour. So as on date, this dream is come into the reality, and in a January, February, or you can say first quarter of a 2025, this plant has been successfully commissioned by us. So the overall project configuration, we have a one alkaline electrolyzer stack of a 5 megawatt, then the hydrogen purification facilities, and the hydrogen which we are generating at the pressure of 14 bar. Finally, we are compressing these hydrogen using the compression facilities up to 200 bar and perfectly integrated with our other business facilities itself. So it's a very simple project configuration. One dedicated solar block of a 6.25 megawatt and directly connected electrolyzer with this renewable power generation facilities. So the total power requirement for the electrolyzer is a 5 megawatt. However, for the balance of plant power requirement in a tone of 600 to 700 megawatt. So why we are saying this is the unique configuration or a unique integration? Because it's a complete off-grid integration. So whatever the power during the daytime we are producing, it's 100% integrating with the hydrogen generation facilities, no grid connection. So our bigger plan to execute the green hydrogen in a tone of 0.2 million metric ton and subsequent ammonia of 1 million metric ton, that project may mature somewhere in a 2031, 2032 itself. To get the basic idea across the available technologies in the market and how its operation and maintenance behave, we established these demonstration facilities. And frankly speaking, this journey was not so easy for us because it's an off-grid integration. So this is the basic columns which we use. First step was the electrolyzer technology selection. So the basic two technologies which are available in the market is one is the alkaline one and the second one is the PEM one. When we enter into the market, we felt that only and only alkaline technology is matured at a major level. However, PEM is already an established one, but at a mega scale, it's very difficult to establish the supply chain issue. So lot of deliberations was done, and as our colleague Mr. Fabio, they just presented a paper what kind of a technologies they have. So we just want to brief that with respect to electrolyzer technology manufacturing, we associated with some of the technology partner, NextCam, or you can say NextClean is one of them. So that's why we know the subject very well. That's why for this demonstration plant, we have selected the alkaline technology and decided as an off-grid integration. Now the basic challenge is how to integrate the renewable power variability in an off-grid mode with the alkaline electrolyzer. So this was a big challenge. So when we conceptualized this study, so lot of our business associates like Honeywell, RE+, they took a good time to establish this concept, and finally when we put it at the field, it take a 3 months to streamline it itself. And to make this concept successful at a day one, we have decided, because it's a off-grid, so battery energy storage system is must. So parallelly, we have considered a 1.2 megawatt of a battery energy storage system. So as on date, in existing operations, the electrolyzer operates with the variability of the power. And if there is a variability in the power, automatically it's simulate the electrolyzer operations. And in the morning hours, as the renewable power or the solar panels wake up, as per the design, automatically it will take a start, and during the evening hours when no solar power is available, automatically it goes into the safe shutdown. However, battery backup always will be there to establish the emergency power requirement during the non-solar hours itself. So these are the basic troubleshooting columns which we have achieved during establish all the basic chapters across the whole field. So electrolyzer operations, frankly speaking, it was very easy to start and stop. It's not a challenge. Whatever the hydrogen we are producing, we are getting a full-fledged purity in a range of 99.999. So no concern. As well as pressure profiles are concerned, it's absolutely matching. It's not a big concern. We are generating the product hydrogen at a pressure of a 14 bar. And the pre-commissioning, commissioning, I mean, it's a very standard chapters across the, chemical and the process industry. So no big challenge was to establish it, this one. The basic where we felt, because it's a daily start and stop operations, so in the mornings, tentative 15 to 20 minutes, same way in the evening, it's around 30 to 35 minutes. It's an unproductive hours for us. So we already earned our experience of a more or less 1 year. So now we can conclude, or we can say, yes, continuous operation of electrolyzer is a must. Daily start stop at a demonstration plant can be achieved or can be successfully, concept can be materialized into the reality, but a bigger level, lot of challenges will be there. So that's why, for what basic lesson learned we have from this particular demonstration plant, that at a bigger size, we will not going to start stop of the electrolyzer. We will operate the complete electrolyzer integration system on a 24/7 basis. Otherwise, whatever the hydrogen we are going to generate, in a tone of 10 to 12% straightforward loss will be there on a daily basis in terms of renewable power. So it's a basic and a good lesson learned for us also to establish or to execute the bigger size of the plant at the West Coast itself. And the final one is the process automation. So process automation, basically how you design your energy management system, who can take care your variability of the renewable power with the electrolyzer operations itself. So this is a key parameter. So that's why in a process automation, whatever the algorithm was designed by us or written by us, ultimately when we comes the overall concept into the operations, is all failed. Frankly speaking, all failed means whatever the logic written by us, it never help us to operate the plant in a continuous manner itself. So that's why, with the help of all experts, it took 3 months again to design the algorithm, and after further a couple of months, the whole concept was stabilized. So we commissioned this plant somewhere in a January, February 2025, and finally the whole concept will become at a stable operation somewhere in a July or a August 2025. So now we are very happy because the whole concept is running as per the renewable profile. if there is a variability in the renewable profile, automatically we are getting or adjustment in the electrolyzer back to back. So which give us a good confidence to establish our bigger size of the plant. And this is lot of big because this is not a profit center for us. This is a basic trial center for us. So whatever the concepts are there, that how the electrolyzer performance with respect to the light temperature. So we did a lot of trial. We maintained the light temperature in the range of 50 degree, then 55 degree, then operated for a couple of weeks, then 60 degrees, 65 degrees, 70 degrees. So finally we realized that the optimum temperature band for the alkaline electrolyzer in the range of around 68 to 75 degrees C. So clear cut there was a difference when we operated our electrolyzer in the temperature band of 50 to 55 and then close to 70 degrees C. Straightforward, there is a gain of, in terms of efficiency, it's around 4%. So all such kind of learnings, first of all, we are ready to share with all of you, and because it's a demonstration plant, so it's an open invitation to industry also. If you want to visit our facilities, it's always welcome to you. Anytime you can contact to me. Then second, a good one, always everyone is talking about crossover, because electrolyzer need to operate in the range of 30 to 110% or 30 to 100%, no need to operate in the range of 20%, 30%. Turn down, someone claimed yes, turn down can be 10%, 20%. But frankly speaking, when we operate the electrolyzer in the range of 20%, 25%, or 30% itself, the huge crossover will be there. I mean, it's very difficult to get the purity. Always the oxygen content in the product hydrogen is more. So it's, and when the electrolyzer, the basic operations in the range of in between 50% to 80% or 50% to 100%, you can say, the best result you will achieve or we will already achieve. We establish our overall operating parameters. Yes, this is the best operating range itself. And this is the major key takeaway which we already discussed, or if you want, I mean offline anytime, we can discuss it with you. And this is the basic concept which we have developed. It's just an overview. It's a 5 megawatt of electrolyzer stack, and then all the fire water facilities, dim water generation facilities. So it's a complete concept today which is a reality. So thank you very much giving your attention, and again it's an open invitation. Anytime if you want to visit our site, it's a most welcome, and thank you very much to all of you.
So we have finished the presentation because one presenter is missing. So thank you very much for your attention and to all the speakers for their very interesting, insightful presentation. I hope to meet you all and have a nice one. Bye-bye.